Hello everyone. In this video, I am going to discuss Network Measures Unit 4 of Social Media Analytics. Here you are studying different network measures like centrality, transitivity and reciprocity, balance and status, and similarity. So first we deal with the centrality. So before starting with the centrality, let us discuss some example like most of you know the cloud score. Cloud score is of Barack Obama is 99, Justin Bieber is 92, okay, Warren Buffett is 36. So what is this value? How you are deriving this value? So this is nothing but the social media analytics, or you can say a centrality measure. It is really very difficult to measure the influence. The cloud score is normally from the range of 0 to 99. So 99 is actually the maximum score, and it indicates that Barack Obama is the most influenced person on the social platform. So this number is indicating the influence of a person. Now we'll start with the discussion regarding the centrality and other measures. The normal questions which are come in our mind is how to find the answer to these questions. Who are the central figures or influential individuals in the social network? What interaction patterns are common in friends? Who are the like-minded users, and how can we find these similar individuals? These are normally a research questions in social media. So how to give the answers to this question? So for every question there is one measure, network measure. Suppose if you want to find who are the like-minded users and how can we find these similar individuals? So there is a similarity measure. With the help of similarity measures, with that network measure, you can answer this question. Then what interaction patterns are the common in friends? For that there is a reciprocity and transitivity. And who are the central figure in the network? To answer this question, you must know the centrality. Okay, so to answer these and similar questions, one first need to define measures for quantifying centrality, level of interactions, and similarity among others. So we are going to deal with all these network measures one by one: centrality, reciprocity and transitivity, balance and status, and similarity. Okay, so first we deal with the centrality. Centrality defines how important a node is within a network. There are two types of centrality: individual centrality or a group centrality. Centrality in terms of those who are connected to you. There are different types of centrality. Individual centrality. The first one is a degree centrality. Degree centrality ranks the node with more connections higher in terms of the centrality. So CD of VI. Okay, so for vertex I, what is the centrality? D stands for the degree centrality and the C stands for the centrality. So CD of VI is equal to DI. DI is the degree of node VI. Okay, so here degree is nothing but the number of friends. You have to visualize the social network in terms of the graph. Okay, so for every vertex there is a degree, and this degree is nothing but the number of friends of that vertex. Vertex is the user or the person on a social network. Let us take an example. Suppose this is one graph. In this graph, what is the degree centrality for V1? Any guess? It's very simple. Okay, so number of edges which are for this node is nothing but the degree of that node V1. It's a undirected right? There is no direction. So for count all the edges, and that is nothing but the degree of the V1. And the degree of all other vertices V2 to V9 all are having the degree 1. Okay. So this is the simple term degree centrality. Similarly, you can use the degree centrality for directed graph. Here we can use the in degree, the out degree, or the combination of the degree as a centrality value. In practice, mostly in degree is used. So CDVI is DI in, that is, it indicate the prestige. Okay, so having more in degree for a vertex means that is a prestigious node. Whereas if the out degree is more, means that is a gregariousness. It shows the gregariousness, means that person is very social. There are many out connections, means it indicates that the person is very social on the network. So total degree may be the in degree plus out degree. So this is for directed graph. Normally we are normalize the centrality. Okay, so how to do the normalization? That is CD norm of Vi is Di upon n minus 1. So you have to count the degree of a node divided by the number of node minus 1. You can also normalize by the maximum degree. Also you can normalize by degree of sum. So these are the corresponding formulas. Now we'll see one example. This is one example of a directed graph. Now you have to find out the centrality of the node. Okay, so for the node A, what is the in degree and out degree? For node A, there is only one in degree and the 3 out degree. So how you can measure the centrality? Normalize centrality. How many nodes are there? Total nodes 1, 2, 3, 4, 5, 6, 7. Okay. So how you can come with the centrality 1 by 2? Here the centrality is calculated as the degree out degree of a node divided by number of node minus 1. So number of nodes are 7. 7 minus 1 is 6. So 3 by 6 means 1 by 2. Okay. I hope you understand it. Now next is for the B. Now what is the in degree for B? It is only 1 and the out degree is 2. So 2 by 6 means 1 by 3. Okay, so in this way you have to calculate the centrality for the directed graph and you can rank the node. So the centrality whose centrality is more is the most, is having the highest rank. Okay, is the most important node in the network. Now we'll go ahead. So here we are using the formula. Okay, this Di upon n minus 1. So you have to remember this formula. Now it's the same graph, but now it is a undirected graph. So you have to calculate the node and its degree and its centrality. So centrality is degree upon the n minus 1. So it is 2 by 3. So it is 2. Okay, so rank is 2. In this way, this is the C. If you observe this C, its degree is more. It's 5 degree. So it is connected to maximum node. So it's obviously it is the most central node in the network as per the degree centrality. Now the next centrality is eigenvector centrality. Having more friends does not by itself guarantee that someone is more important. I hope you understand it. What I want to say. Having more friends does not by itself guarantee that someone is more important. Suppose if I have many friends, 100 friends, means it's not indicate that I am very important or influence person. Having more important friends provides a stronger signal. But when I having a friend with the most important person. My friend is most important person. Then it provides a stronger signal. So the next type of centrality, that is eigenvector centrality, generalizes the degree centrality by incorporating the importance of the neighbors. Okay. So now we are involving the neighbors while calculating the centrality. For directed graph, we can use incoming or outgoing edges. Let us assume the eigenvector centrality of a node is CE Vi. We would like CE Vi to be higher when most important neighbor, that is node Vj, with a higher CE Vj point to us. Incoming or outgoing neighbors? For incoming neighbors, it is Aj is equal to 1. We can assume that Vi centrality is the summation of its neighbors centrality. So you have to do the summation of the neighbors centrality to calculate the. We have to normalize this summation by the some fixed constant, that is 1 upon lambda. Summation of j is equal to 1 to n Aj Ce Vj. We can rewrite the formula in terms of matrix C V1 V2 Ce Vn T, where a raised to t is nothing but the adjacency matrix of the graph. Lambda is a constant and it is a corresponding eigenvalue. So here the question is, which eigenvalue and eigenvector pair would we choose? So finding the eigenvalue by finding a fixed point method. Start from the initial guess. Example, all the centralities are 1 and iterative t times. We can write CE0 as a linear combination of eigenvectors Vi of the AT. Substituting this, we get that lambda 1 raised to t is summation of I alpha A lambda I upon lambda 1 raised to t Vi. Lambda is the largest eigenvalue. So here this is a very important theorem we are using in eigenvector centrality, that is Perron-Frobenius theorem. Let A represent the adjacency matrix for a strongly connected graph. There exists a positive real number, that is lambda max, such that lambda max is an eigenvalue of A and any other eigenvalue of A is strictly smaller than lambda max. Furthermore, there exists a corresponding eigenvector V of A with eigenvalue lambda max such that for all Vi is greater than 0. So you have to choose the lambda max such that all the lambda values are less than that value, and it should be a positive number. So to compute the eigenvector centrality of A, what is the procedure? We compute first the eigenvalue of A, then select the largest eigenvalue, that is lambda. Then the corresponding eigenvector of lambda is CE. Based on Perron-Frobenius theorem, all the components of CE will be positive. The component of CE are the eigenvector centralities for the graph. We'll solve one example on eigenvector centrality. This is a very simple graph with V1, V2 and V3. So what is the adjacency matrix? It's very simple. It's 0, 1, 0, 1, 0, 1, 0, 1, 0. This is the adjacency matrix of this graph. Now you can represent it with the lambda CE is equal to ACE, that is A minus lambda I. I is the identity matrix into CE is equal to 0. So you can represent it as 0 minus lambda 1 0 1 0 minus lambda 1 0 1 0 minus lambda u1 u2 u3 is equal to 0 0 0. you have to calculate the determinant of this matrix. So after calculating the determinant of this matrix, you are getting the three values of the lambda. So this first minus lambda into this minus this into this. Similarly, when you are considering this 1, you have to omit this column and this row. So 1 into 0 minus lambda minus 1, and obviously it is 0 means all the terms are 0. So you are getting the lambda values as 0 minus root 2 and plus root 2. So which eigenvalue you are choosing here? That is the largest value and it is positive. So plus square root of 2 is the largest eigenvalue, and you have to consider this for calculating the eigenvector. So you have to substitute that value in the matrix, lambda value, and you have to calculate u1, u2 and u3. So your u1 is 1 by 2, u2 is root 2 by 2 and u3 is 1 by 2. u1 is equal to u3, so it's both the values are same, whereas u2 is root 2 upon 2. So here this is the second example where there are 5 vertices. So it's a adjacency matrix. Then you are getting the 5 values of lambda. Okay, so you have to choose the maximum value, that is 2.68 as a eigenvalue, lambda max, and substitute it and calculate the eigen centrality for each of the vertices. Okay, so in this way the eigenvector is calculated, or eigenvalues is calculated for the given graph. Now before going ahead, there is a problem. If you observe both the problems, in the first problem it is very easy to calculate the lambda value because it is only a 3 by 3 matrix. But when you observe the second matrix, that is 5 by 5 matrix, it is very difficult to calculate this lambda value by using your normal mathematical procedures. So you must know some alternative method or the algorithm to calculate the eigenvector centrality in a simplified way. So in the next video I am going to explain that method of calculating the eigenvector centrality for a complex graph. Thank you.